Hello everyone, welcome to my talk. First, let me introduce myself. I'm Xiaojian from Institute of Micro Nanoscience and Technology, Shanghai Jiao University. My interests are design, fabrication, and simulation of electrostatic actuators. The topic of my presentation is how to suppress the rebound due to waveform deviation for electrostatic switches. The outline of my talk includes 5 parts: background information, the innovative work we have done, fabrication and measured results, conclusions, and the last is a further research. Well, let's move on the first part. A prevalent application for electrostatic actuation is RF MEMS switch, which is widely used in mobile phones, radar, and wireless communication system due to its low energy consumption and high oscillation. This is the two entities of capacitive RF MEMS switches. Construction for RF MEMS switch is very simple and shown in this figure. This is a schematic of classic RF MEMS switch. When enough bias voltage is applied on the electrodes, and the upper electrode will move toward the actuation pan, and the impulse on each end will contact with the transmission line and turn on the signal line. Although the RF MEMS has its unique advantages, the driving voltage is generally high. This is a comparison between conventional switch and the RF MEMS switch. Obviously, its driving voltage can reach 20 to 80 watts. High voltage sincerely affects switches' lifetime due to higher impact velocity and insulation charging. Therefore, for high reliability, one of the focused issues is how to reduce driving voltage and suppress impact velocity as far as possible. In view of the above question, we proposed an inherent variable stiffness approach to reduce driving voltage and suppress impact velocity. Next, a variable stiffness approach will be proposed and shown in the figure 7. This is the prevalent method is a dual pass voltage actuation for a soft landing. Look at this figure 6. First, the actuation voltage is applied for acceleration, and the actuation voltage is removed, and right time for decelerating decelerating to zero impact velocity, and finally a no hold voltage will keep it closed. This is a good method for reducing impact velocity. However, unfortunately, the system has a high sensitivity to waveform deviation. So we proposed inherent variable stiffness approach to reduce the impact velocity and suppress impact velocity. Next, a variable stiffness approach will be proposed and shown in the figure 7. The x-axis is the displacement of the moving electrode. The red line is the spring force, and the blue line is the dual actuation voltage. For fair comparison, the nonlinear and the linear spring has the identical restoration force and the closing potential G0. Obviously, the restoration force for the nonlinear spring is always smaller, so it has a very low actuation voltage. On the other hand, the nonlinear spring is characterized by a rapid increase in stiffness with displacement, which means that the negative work done by the nonlinear spring for deceleration is more concentrated in the second half of the triangle. This characteristic can be interpreted by an energy ratio expression shown in the equation 1. This will improve systems robustness. Let me take a simple example. Supposing that the voltage duration is slightly shortened. For the nonlinear spring, the position with zero velocity will be closer to the collision position G0 than the linear spring, so that the next holding voltage can close switch with very low impact. So the variable stiffness spring has better robustness for waveform deviation. To verify the validity of our method, we try to utilize a clamped guided beam with very simple construction, and show in the figure 9, the left end is fixed and the right end is only free in the y direction. On the large deflection, the guided end can generate a cubical nonlinear behavior due to axial stretching. And shown in figure 12, this is a prototype for RF switch based on clamped guided beam. An interferometric profilometer is used to measure the height profile. The measured electric gap is 7 micron, and the beam thickness is only 2 micron. And the other dimensional parameters are not strict in type 3. Next, let me introduce the testing system. This is a microforce testing system used to measure spring force. Its core component is microforce sensor with 50 nanonewton resolution. The right figure is the tested and simulated result. Obviously, the clamped guided beam exhibits significant nonlinear behavior. And shown in this figure, for dynamic displacement response, we set up a electric and displacement testing system based on solid laser probe, which is used to detect the electric displacement. The bias voltage is applied by a pair of voltage meter probe. The measured dynamic displacement response can be monitored by a oscilloscope. Next, we will present a testing result for waveform deviation. In the test, a dual pulse voltage with 170 microseconds for soft landing is applied on the electrodes. The x-axis is response time, and the left and right y-axis are displacement and velocity, respectively. The blue line is the soft landing response curve. Attention. When the pulse duration is reduced to 150 microseconds, it is obvious that the dynamic displacement response shown in red circle right circle has a slanted rebound. But because of the next holding voltage, finally the moving electrodes is pulled down, and keep the electrodes closed. But for linear spring, its deviation from closing position is obviously larger, which makes the moving electrode not closed under the next holding voltage. Therefore, the sensitivity of the linear RF MEMS switch under pulse duration is significantly smaller. In addition, the driving voltage for the linear spring is only 16 watts, which is 19.5% lower than that of the linear spring. So finally, it is a simple summary. Compared to linear spring, a linear spring can obviously reduce driving voltage, suppress impact velocity, and weaken sensitivity to waveform deviation, which can enable extending of lifetime for RF MEMS switch. For further research, we will commit to design variable stiffness spring with very simple construction and higher order restoration force, such as 5 order or 7 order restoring force. Our ultimate goal is to produce customizable any inherent variable stiffness spring. That's all. Thanks.